Welcome to Module F, Lecture 4. In this lecture, we shall continue our discussion about network algorithms which are related to traffic assignment. In Lecture 3, we said why we need to identify shortest path in the context of traffic assignment, and then one very popular algorithm which is known as Dijkstra's algorithm that we discussed, and also I took an example of a network and then explained to you step by step how you can apply Dijkstra's algorithm to find out the shortest path from one home node to all other home node. Now, in continuation to our same discussion regarding the shortest path, how to find out the shortest path, today we shall discuss about another algorithm which is also very popular, known as Floyd's algorithm. This algorithm is generally, I can say, more efficient, because what we wanted or what we were required to do, say if there are n number of nodes in a network, to get shortest path from one home node to all n home nodes, we wanted n iterations in the Dijkstra's algorithm. Here also it is iterative and we have to follow the iterative approach to get it, but in one round, that means in n iteration, we can get shortest path from all home node to all home node. That is the beauty. So, in Floyd's algorithm, the nodes are as usual numbered as 1, 2, 3, 4, let us say there are n number of nodes, and the distance found at any stage of the algorithm, say when we are considering every stage, we consider an intermediate node. I shall explain you of course, in much more detailed manner with also an example, but every stage we shall consider an intermediate node, and that intermediate node we shall start with considering node number 1, and then every stage we will increase it by 1. So, then number 2, number 3. So, if I say generally we are considering a node k, where k may be any number between 1 to n depending on what is the iteration number. These the distances are stored in a n by n matrix, because as I said we are dealing with shortest path from all home node to all home node. That means 1, 2, 3, 4, like that if there are n node from each of these home node to all other home nodes, we are trying to find out the shortest path. So, we are actually storing that distance data in a matrix called dk. K indicates that it is the matrix at the kth iteration with elements dk I j. It is a 2-dimensional matrix from node I to node j, we are finding out the shortest path. So, these values are stored, and the arc length of the network will be formed the final matrix. The final matrix will of course be coming out at the end of nth iteration. So, that will be d n, and the initial matrix whatever we are going to assign in the beginning, that we call it as d 0, that is the initialization, and then we keep updating these matrix cells as and when they are required or contextual. And finally, by the time we go to nth iteration, whatever will be the d n matrix, that is the final shortest path. And remember that I said that in every iteration we are considering an intermediate node, right. So, every node is actually considered as an intermediate node. Similarly, the initial predecessor also we shall store in again a n by n matrix, but that cell will denote what is the predecessor. For example, if I consider a cell 1 to 5. So, let us say we are considering about from 1 to 5, then this cell value will indicate what is the immediate predecessor node of 4. That node is stored. Suppose predecessor node of immediately 5 is, say let us 3, then we shall take 1 to 3, that cell will take what is the predecessor node for 3. Like that we can backtrace and finally, we can come back to the home node, whatever it may be, in this case 1 or maybe from 2 to another node we are talking, accordingly it would be. So, there also every iteration, as we are updating the distance matrix, wherever any cell we are updating in the distance matrix, then we are also updating the corresponding cell, particularly the predecessor, in the Q matrix. So, Q also will finally have Q n, which is the final predecessor matrix. Now, how to go about it? How to apply this algorithm? We shall apply this algorithm step by step, or again as I said, it is an iterative approach. First, step 1 is kind of initialization. How we are doing the initialization? We have n by n matrix, that matrix we are calling as D0 matrix, and there will be elements D0 I j from node I to j, the shortest path we are talking about. That will be equal to D I j if arc I j exists. Suppose 1 to 3 we are talking, if 1 to 3 there is a direct connection, then whatever is the value we know, that value we shall put here. It will be 0 if I equal to j. So, all the diagonal elements will be 0, 1 to 1, 2 to 2, 3 to 3, all will be 0. And if there is no direct connection, suppose one is not connected directly to 3 in my network, then I do not know what is the shortest path. So, I will assume that this is infinity, the length is infinity. Infinity means I am actually assuming a very high value. You can as well assume a very high value, which is higher than any of the length of any of the link in the network. So, we that way we create that D0 matrix, and I explained how we consider the element. Now, in the similar manner, we also create a n by n matrix, which is predecessor matrix, and since this is the initialization, that will be Q0. Now, how this element or how we consider this element? We will say Q0 I j equal to I, because what we explored in the distance matrix, suppose I considered home node 1. So, I said 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, like that up to 1 to n, and in each case I took the length of the link if there is a direct connection. If there is no direct connection, then we do not know. So, I assume the cost as infinity. That means, in all these 1 to all other node, for all the nodes, target nodes or destination node, the predecessor is I. Okay? So, that is what it is. So, first what will happen? 1 to all other node, all predecessor is 1, 2 to all other node, all the predecessor value for each destination cell is 2, 3 to all cell 3, like that. So, that is what is my initial distance matrix and initial predecessor matrix. Now, with this we go to the next step, step 2. Now, let k be the intermediate node in the shortest path from source to destination, and now we shall increase k by 1. So, k was initially, as you said, Q0 D0. So, k was also assigned initially as 0 value. I could have mentioned in step 1 also, but I mentioned in the beginning of step 2, and then now we are going for iteration. So, I will increase k by 1 value. So, k will be taken as k plus 1. So, when I am going for the first iteration, what will be my value of k? Value of k will be 0 plus 1 k. When I go to the second iteration, then what will be my value of k? K was already 1. So, now it will be taken as 1 plus 1 2, like that. So, whatever will be the k value, k is, since it is 1, now we are definitely trying to get a distance matrix which will be the D1 matrix, and also the Q matrix which will be the Q1 matrix. So, how to get the D1 matrix? Generally I am saying, if I am trying to get the dkij, k in the first iteration is obviously 1, but generally dkij is minimum of, carefully observe, you can understand all the things very easily, minimum of 2 values. What are the 2 values? So far what is my value? My value is d k minus 1 I j. In the previous iteration, whatever was my best value. In this case, if I am the first, if I am going for the first iteration, then what was the d 0 I j? That will be the fourth iteration, it will be third iteration d 3 I j, fifth iteration it will be fourth iteration value. So, whatever till now, whatever is the value, best value I have taken, I am comparing that with another value. What is that another value? I am saying d k minus 1 I j I to k and d k minus 1 k j. That means, earlier if I try to explain you further, say I have I here, I have j here. So, I said what is my best I j till now we got in the last iteration, and then I am bringing one iteration k and I am saying whether d I k plus d k j. This k is the basically intermediate node that I am currently considering. This is I and this is j. Okay. So, if I find still my d I j, whatever was there in the previous iteration, that is the shortest path, then by travelling from I to k and then coming from k to j, I am not able to reduce my distance. So, I do not update the value, whatever was my d k minus 1 I j, that remains as a value in my d k I j. But if I find that d k minus 1 I k plus d k minus 1 k j, that means travelling through k instead of travelling from I to j, whatever may be the present update we got, they may be direct, may not be direct also, but what is the best value so far we got, I am only exploring that value is better, or I can travel from I to k and then come back from k to j, that is better. Now, if the second one is cheaper, then what I will do? I then need to update my matrix. So, now then my d k I j will be d k minus 1 I to k plus d k minus 1 k to j. Addition or the total distance, that will be my new shortest distance from I to j as far as we have explored, and till kth iteration, that is the best value. Now, again if the first one is taken, that means d k minus 1 I j, I find that my earlier solution is better, then the predecessor matrix also I do not update, because my predecessor matrix also does not change. But if I change the or accept the latter value, that means d k minus 1 I k plus d k minus 1 k j, that means I am now not travelling directly, but I am now coming via k or through k. So, my predecessor node for j becomes what? K instead of the present predecessor. That present predecessor also may not be I, because that may be in later iteration, first iteration it will be I, but in the later iteration if I have explored another intermediate node better, then my predecessor value is stored there, okay, that node. but now whatever is my k value I will update it. Clear? So, with this, that is what I say, my q I j will be q k minus 1 I j if minimum d I k equal to d k minus 1 I j. And if I take the latter one, that second part becomes the cheaper, then I change the predecessor value and I make the predecessor of j as k. See how intelligently it is done or how efficiently it is done. Now, k value is changing from 1 to n. Can you just imagine what is happening actually? So, iteration to iteration, first suppose say 1 to 7 or 1 to 5. So, what I will do? First I am checking if there is a direct connection 1 to 5, I am saying okay, that is my best. Then I am checking 1 to 2, 2 to 5. Then in the next iteration I am checking 1 to 3, 3 to 5. Then in the fourth iteration I am checking 1 to 4, 4 to 5. Like each intermediate node, I am checking whether travel via that or through that intermediate node, whether I am able to reduce my distance. If I am able to reduce my distance, then I need to update my matrix. If not, then the same solution I shall keep. And if I am updating, if I find that traveling through this new node, what is the intermediate node k, is actually I am able to reduce my distance, then I also need to update the predecessor matrix. That is all, very simple. Now, let us take an example. You can see this network and I shall show you how you can apply Floyd's algorithm to get your shortest path matrix, final shortest path matrix and final predecessor matrix. Let us first go with D 0. So, let us say 1 to 2, you know there is a direct connection. So, 1 to 2 value is 8. So, I have put it 1 to 2 is 8. 1 to 3 also there is a direct connection 3. So, I have put that value 3. 1 to 4 also there is a direct connection, the value is 5. So, I have put the value of 5, but 1 to 5 there is no direct connection, you can see. So, that cost I do not know. So, let us I want to assume a very high cost, infinity. Similarly, all other cells you can fill up, say 2 to 1 8, 2 to 2 obviously diagonal elements all will be 0, 2 to 3 2, but 2 to 4 again there is no direct connection. So, it is infinity, and 2 to 5 there is a direct connection. So, value is 5. Like that I follow for my D 0 matrix, initial matrix. Then what I do? I have to also make my Q 0 matrix, predecessor matrix. You see, from home node 1 to all other node 1, all cells 1, from 2 to all other destination nodes 2, 3 to all other destination node 3, 4 to all other destination node 4, 5 to all destination node 5, because my distance matrix is based on that, you know, every time every row we take with that origin point, okay, or that home node. So, that is what is my predecessor, right. So, I am ready with my D 0 matrix, I am also ready with my K 0 matrix. Now, the K will be assigned initially as 0 and I will now increase the K by 1. So, K will be 1. So, now what then I shall do? I shall check everything. Now, in the first row obviously nothing will change, because I have already taken 1 to 2, 1 to 3, 1 to 4, 1 to 5. Okay. So, K is also 1. So, in the from 1 to all other home node, this will not be anything different, right. So, obviously, my cells will not change. But look at this, 2 to 1, 2 to 3, 2 to 4, okay, and I have said what are my values and I want to take the minimum. You see, when I think 2 to 4, initially what was the connection? 2 to 4. 2 to 4 was infinity. There was no direct connection. But now when I take 1 as my intermediate node, then I am exploring 2 to 1 and 1 to 4. So, when I take 2 to 1 and 1 to 4, I find the total cost is 8 plus 5, 13. 13 is less than infinity. So, I update my cost. Now, that particular cell I shall update, and I also have to update then for 4, the predecessor node will no more be 2 to 4, the predecessor node will not be 2, but it will be changed to 1, correct. Same way you find D 4 2, there was no direct connection, but when I travel through 1, 4 to 1 and 1 to 2, then my cost is 14. So, 14 is less than infinity. So, I update my cost and I have to change my predecessor for node 2, destination node, and home node 4. So, 4 to 2, if I have to travel, I know now my predecessor node for 2 should be 1 instead of 4 directly, that I need to update. 4 to 3 also, there was no direct connection, the cost was infinity, and I find I can travel from 4 to 1 and 1 to 3 with a cost of 9. So, these are the 3 cells which can be or should be updated, and the corresponding predecessor cell also will change. So, let us see that. You can see here I have shown now the D1 matrix, and the cells which have been updated, I have marked those cells using red font, red color. So, you can see 2 to 4 and 4 to 2, 4 to 3. These are the cells which were in D0, they were all infinity, they are now changed, and because I got a better solution than infinity. So, I have explored, but not everything we could explore. Still you can see in this matrix there are lot many other cells which are still infinity, because to those cells neither there is any direct connection nor there is any direct connection through 1, right. Say for example, 4 to 5 is still infinity, that means 4 to 5 no direct connection, and 4 to 1 and 1 to 5 also I cannot do, because at least I am sure I do not see the network here, but at least one of those links or maybe both links are there is no connection, direct connection. So, I do not have, or so far nothing better, there need not be even a direct connection, because as we proceed this all getting updated. So, direct connection may vanish after some time, but whatever is my best solution till the previous iteration, in this iteration we could not get a better solution than what I already got till my previous iteration. So, I do not change those cells, right. So, I have my D1 matrix is available. Now, the cells where the distance has changed. Why the distance has changed? Because we discovered that if I travel through 1, then to all these nodes which are marked red, distances are shown as red, then I am able to reduce my cost. So, obviously, I have updated. So, now the predecessors are also updated. You can see the corresponding cell, the predecessor node has become 1, because my k was 1. Now, similar way I will now increase k by one more value. So, I will check each case if 1 to 3 is better or 1 3 3 2 is better. If 3 2 is better, 1 3 plus 3 2 is better, then predecessor of 2 will be changed from the previous one to 2. So, like that I have shown here the corresponding D2 and Q2 matrix, D3 and Q3 matrix, D4 and Q4 matrix, and D5 and Q5 matrix. Okay. So, each cells wherever the changes are done are also indicated using a red font. So, those are the cells, and you will see in all cases the corresponding predecessor cell is also changed depending on what is the queue. So, like that, by the time you have reached to the nth iteration, you have explored actually all possibilities. So, whatever is my D matrix now, Dn, all elements whatever I got inside, they are the best value. I cannot improve anything, because all possibilities I have explored. Similarly, that is what the predecessor. And how to backtrace? Suppose you find, let us take a solution 4 to 5, the predecessor is 3. So, I know 5 is coming from 3. Now, I shall take 4 to 3, what is the predecessor? Right? I find it is 1. So, I know 3 is then coming from 1. So, 5, 3, 1, and what is the predecessor for 1 is 4. So, 4, 1, 3, 4, 1, 3 and 5. That is the path, and the cost is correspondingly, we are talking about I 5, I 4, J 5. So, corresponding value is 16. So, 16 is the total cost. Fine. Now, another approach is also used, what is called diversion curves. It empirically represents empirically derived relationship of the proportion of traffic that are likely to be diverted to a new facility, most cases once they are constructed. So, these models are based on, they consider many factors, say what is the travel time saved, what is the distance saved, sometimes they take travel time ratio, sometimes take travel distance ratio, sometimes take both distance and speed ratios, sometimes may take cost ratio. Based on all this thing, they give then what is the proportion of traffic that are that will get shifted to the new route based on these values. As I say, multiple things are there, but remember, they are not able to simulate the behavior of traffic on the entire network, but mostly used when you are just considering maybe a road passing through a town and you construct a bypass route, and you want to find out how much traffic will get diverted to the bypass. You can use simple model like the diversion curves. Many people, many researchers have developed such kind of curves, and whatever, if it is based on speed ratio, cost ratio, time ratio, or the distance saved, time saved, whatever is the based on what value the diversion curves are developed, you can accordingly use the diversion curve to get the proportion of traffic. That means, we are not doing any formal assignment, but just getting how much grossly the traffic will get diverted based on these factors. Now, one such diversion curves I have mentioned here is the California curves model, which actually use time saved and distance saved both. So, x axis wise you select, once your consideration, if we travel by a freeway, okay, a access controlled road, freeway, what is the time saved vis-a-vis what is the distance saved. So, once you know the time saved and the distance saved, you can select one of these appropriate curves based on speed, and then you can select an appropriate curve and then find out what is the. So, you know the time saved, you know the distance saved, accordingly you can find out what is the proportion that will get diverted. Now, some people may consider even a third parameter, fourth parameter, accordingly various representations are there. So, but basically these are the aspects which are considered. Some may consider only based on travel time ratio, some may consider cost savings, time savings, distance saving, distance ratio, many factors people consider, right. And based on those, once you know my proposed facility value, my new existing or the current facility value, then what is the saving or what is the ratio in that whatever factor is considered. Then from the graph you can say, okay, my 20% traffic will get diverted. Similarly, Detroit model is also another model which takes speed ratio and distance ratio. So, as it takes it took travel time savings and distance saving. So, similarly Detroit model says speed ratio and distance ratio. So, if you know the speed ratio, if you know the distance ratio, you can find out how much from the diversion curves you can find out how much will be the shift of the traffic to the new route or proposed route. Okay. So, in this lecture we discussed about the Floyd's algorithm. I explained you how the algorithm works and also tried to explain you with an example problem step by step how you get. Then also introduced to you the approach, another approach for traffic assignment, which is diversion curves, and what is diversion curve, what are the kind of parameters they use to estimate the diverted traffic or proportion of traffic which are likely to get diverted, and two particular models I mentioned, one is the California curves model and another is the Detroit model. So, with this I close this lecture and thank you so much.